So believe it or not, I know we've done some simple problems with male and female children and some dice and cards, but actually classical probabilities are really difficult. We're doing kind of the most basic, but they can get very tricky very quickly. So it would help with classical probabilities if we had some way of knowing how big the sample space was going to be before we started making some kind of tree diagram. Because tree diagrams are only useful if it's a pretty small sample space size. So the multiplication of rule for counting will do this for us, but only with classical probability questions where all outcomes are equally likely and all that stuff. Okay, so this is actually a little bit from section 5.5. We don't cover much of 5.5, but this is one thing that it is valid to know and you should know. And I'm just going to sneak it into 5.1 instead. All right. So how large are the sample spaces for the following probability experiments? Use the multiplication rule of counting to calculate and show your work. So you're going to toss a coin 3 times, a fair coin 3 times. So each coin toss, there's 2 outcomes, heads and tails. And then you toss it 1 time, there's 2 outcomes. The second time, there's 2 outcomes. The third time, there's 2 outcomes. 2 times 2 times 2 makes 8. Okay, suppose you were going to toss a fair 6-sided die and then a fair 20-sided die. Yes, there are such things as 20-sided dice. Hold on. There we go. This is the Wikipedia page on dice. And this one over here is what it looks like. It's one of the Platonic solids right over there. Okay. It's called an icosahedron. They mention it down here. Okay, so let me go back. This one. All right. So you are going to do that. 6 times 20 makes 120. All right, suppose you're going to select a card at random from a standard poker deck, then replace it, shuffle, and then draw a second card at random. So there's 52 cards for the option for the first card and 52 for the second card. When you multiply them, 52 times 52 makes 2704. All right, now what about Yahtzee? Oh, I already did that one, I think. Well, if I didn't, there it is. Sorry, I had students right outside my door. I had to answer some questions. Okay, so let's go down to having 3 children. So we've made a tree diagram once for having 2 children. So suppose you're going to have 3 children in the future. What could be their genders? So again, it's 2 times 2 times 2 because there's 2 genders possible and there's 3 kids. So 2 genders for the first child times 2 genders possible for the second child times 2 for the third one, which makes a total of 8. You are going to construct the sample space using a tree diagram, and I've already done it. So the sample space is actually this part over here. Maybe I should put it in like, I don't know, a different color. Let's see here. Purple. There we go. All right, so that part's the actual sample space, and the rest of it is just the diagram helping you figure out what this should be. So the purple part's the part you really are looking for, and then everything else is just you trying to figure this purple part out. Okay? Maybe I should box it or something. Makes it obvious. Boom. That's the answer. All right, so here's the sample space. There's the diagram. So you can see like you had a male for the first child, male for the second child, male for the third. That's male, male, male. Male for the first child, male for the second, female for the third. That's male, male, female, and so on. All right, what is the assumed probability for each outcome in the sample space above? Well, there's 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. So 8 possible outcomes. So that would be 1 out of 8 because you assume that all 8 outcomes are equally likely. All right, so if that's the case, what's the probability, and I know, of having exactly 1 girl? Okay, so exactly 1 girl, that's male, male, female, male, female, male, and female, male, male. Those 3 options. So that's 3 options out of a total of 8, and that's 0.375. Okay, I don't know what I was doing there. Alrighty, now what about empirical probabilities? Let's leave classical ones aside for just a little bit. So classical, again, are hypothetical. You just imagine how it works and you set up a tree diagram or something to organize yourself. And just for the record, you don't need a tree diagram to do this. You could think of these on your own, then more power to you. You just want to do it in a way that's organized, and the tree diagram helps organize us. Okay, so if we don't have that, what if we have things that come from data? So we've actually done an experiment We've gone out and conducted trials, that kind of thing. So instead of imagining coin tosses, what if you take a coin out of your pocket and really toss it? That's empirical data. Empirical should sound familiar to if you've ever been in a science class. That's kind of what you're looking for in science, in labs, is you're looking for empirical results, things that actually occurred that you watched with your own little eyeballs. Okay. Okay, so this probability is often used in statistics because it's based on past data. All right, statistics, of course, is all about gathering data. So if you can gather that data, then you can use it to make probability assumptions. The classical stuff is really more for gambling, to be honest with you. Gambling, games, that kind of thing is classical stuff as a general rule. Empirical is more like data. I gathered, well, for example, this is the number of graduates from Jackson Community College from spring 2010 to winter 2011 by degree. Here they are. I got it from the website. So we are going to find the probabilities, and yes, we're going to use Excel to do this because we don't want to do all this by hand. It's annoying. Now, of course, on your test, might you have to do this by hand? Sure. I mean, it's not hard. It's just, I'm just going to use Excel to kind of get me out of doing some of the heavy lifting here. But this is a simple enough problem that you could do it on any exam with just a basic calculator. So what you need to do is you need to find the sum. So equals the sum of these numbers. So you can say, oh, okay, we had 1077 students that graduated in that year, that academic year. So when I want the probability, what I want is 66 divided by that total. And give it dollar signs. That way when you drag it, everything will be great. So drag. And if you did it right, the sum should make 1, which it does. Beautiful, huh? Okay, so again, this should look very familiar to you because we did this. We did it in chapter 2. This was called a relative frequency distribution. Sorry, this is 5.1 example. Oops, that's not this year. Hold on. Aha, example 9. Oh, I don't need that either. All right, 5.1, there we go. Example 9. Cool. All right, so we have our probabilities right here. And again, how did I get this? I divided 66 by the total. Enter. The next one's 511 divided by that total, and so on. And of course, you could do it yourself with a calculator. You just need to add these up and then divide each one of these on your own. All right, I'm going to copy and paste because I'm lazy. I'm going to go back to my spreadsheet right here, and I'm going to copy and paste those values in right there. All right, so I computed the probabilities for the third columns. Oh, it said to do it as fractions as decimals. All right, I'm just going to write it. This one's 66 divided by 1077, right? This one was 511 divided by 1077. Oh, man. All right, hold on. There we go. I've got them all in there. And again, the fraction things, just so you know where they came from. This is exactly the kind of data set we would use decimals with as a general rule. All right, why are these probabilities empirical, and are any graduate degree types unusual? All right, well, I just typed them up for a sec. So why are these empirical? Well, empirical is based on data, and these numbers came from the actual institutional research department at JCC. These are real numbers from real students, right? You didn't just hypothetically think about, oh, 1, 2, 3, 4, 5, 6, 7. I mean, if this was classical, you'd say, oh, these are all equally likely, so everything's got a 1 in 7 chance, right? But empirical goes, no, 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 no. We don't assume anything's equally likely. We gather data and figure it out, right? In fact, I just wrote that up. So classical probability would have assumed each degree had a 1 out of 7 chance because there's 7 degrees. Empirical actually gathers data. Now, are there any that are unusual? Yes, there are. There's associate in science, because there's only 24 out of 1077, which is a probability of 0.022, which is less than 5%. And this concentration thing is right on the border, but it's less than 5%. It's less than 0.05. So those two are unusual. None of the rest of them are. Okay? All right, I'm going to start example 10, but we're not going to finish it. Not right yet. So we'll set it up, and then we will finish it in the next video, I'm thinking. So let's see here. Okay, so I want you to imagine that you toss a coin and then toss a six-sided die. Okay, how large would the sample space be? So use the multiplication rule of counting for that. You know that this coin has two sides. The die has six sides. 2 times 6 makes 12. All right, now construct a sample space. Now realize you're going to have 12 items in the sample space, right? Use H and T and 1 through 6. And there it is. So you've got heads. You could have rolled heads and then a 1, heads and then a 2, heads and then a 3, and so on. Tails 1, tails 2, tails 3, and so on. So there's the sample space over here. It's got 12 outcomes in it, just like we said. If that's the case, what's the probability of rolling H1? Well, there's one H1 out of 12 total, so that's 1 out of 12, which would be 0.083 repeating in a decimal form. All right, now let's continue, and we're going to toss a coin and a die ourselves, and we're going to do it with StatCrunch, I believe. So hold that thought. All right, I went to StatCrunch, your handy dandy StatCrunch, available for free. Everybody loves it. And what I did was I typed in the six outcomes for heads, six outcomes for tails. That's 12 outcomes. And I just wrote outcomes at the top. Now, what I want to do is data, and let me find it in here. Oops, I found it. I knew I had seen it. It's sample columns. I want to take a sample from that column. So there it is. So click sample columns. And then I say outcomes. And then I say what I want. Well, I only want to pretend that I tossed it one time. So sample size is 1. I don't have to worry about with replacement, although I would be doing this with replacement if I had to. So whatever. And then I can say sample the column. And there it is. It put it into column 3 for me because I've already done it once. And that's fine. I can shut that. All right. So it gave me H1. There we go. All right. So let me go back. So I can circle which one I got. I got H1. Boom. Now you get whatever one you've got, right? So then how many trials of the experiment were H1 in the class overall? So I'm actually going to simulate that. So let's go, we'll pretend you have a class. So I'm going to sample columns. I'm going to sample with replacement, and I'm going to assume we have a class of size, I don't know, 30. So I want samples of size 30. I want to do it with replacement because everybody's got to have an equally likely chance of getting all of these. And then I can say, oh, I don't want to split it across the columns. I want it stacked with a sample ID. There we go. Splitting across the column is going to make each one its own person, which we don't really want. Okay, so I'm going to stack with a sample ID and say sample column. Oops, I forgot to tell it which column to do. That's not good. There we go. So I have it under outcomes right there. So outcomes is the sample as the group I'm coming from. I'm going to get a sample size of 30 because I'm going to pretend there's 30 people in our class stacked in the sample. And there we go. There they are. So you can see I've got a T5, a T2, and so on. And now everybody who does this is going to be slightly different from each other, right? Okay. So if we go back to our page, it'll ask us how many trials did we do? Well, I did 30 because I pretended there were 30 people in the room. Oh, excuse me. I take that back. There's 30. This is 30. This one's 30. This one is how many are H1. So let me show you how to sort your data. So you go back to StatCrunch. You go to data, sorry. And then there should be a sort column. There we go. Sort that column. It's not the first one I did. That was the singleton. It's the second one I did. That was the group, right? Sample outcomes, and say sort column. And it sorted it for me right there. And I can see that I had 3. Now you might have a different number than me, but I've got 3 of them. Okay, so for me, it was 3 out of 30, which gives me an empirical probability of 3 out of 30.10. All right, let's pause right there, and we'll be back to keep working on this problem and our Excel spreadsheet for it. All right, I'll see you in a bit.